Welcome to this episode of the Structural Engineering Channel, a podcast focused on helping structural engineering professionals stay up to date on technical trends in the field and to help them succeed in their careers and lives. In this episode, I'll be talking with Logan Mullaney, president of InQuik USA, about the innovative InQuik bridge system, the system's global expansion, and the future of bridge construction. I'm your host, Matt McCardle, and before we get started, here's a quick word from our sponsor for this episode, PPI, a Kaplan company.
This episode of the Structural Engineering Channel is brought to you by PPI, a leader in engineering exam prep for the PE structural exam. PPI provides expert prep courses and study resources designed to help you pass the PE structural exam the first time. PPI's PE structural course is fully updated and taught with October 2021 code references and includes new editions of their PE structural books. PPI's live online courses include hours of lectures, problem-solving demonstrations, exam strategy sessions, office hours, and a passing guarantee. When you take a live online course, PPI guarantees you will pass, or you can take the on-demand course for free. PPI has helped engineers achieve their licensing goals since 1975. Check out PPI today at PPI2pass.com to see all of the resources available for PE structural exam prep. Again, that's PPI2pass.com.
Logan, thanks for joining us. Could you tell us a little bit about your journey from the early days at InQuik Australia and then becoming the president of InQuik USA?
Yeah, so thanks, Matt. And it's been a really interesting journey for us. We ended up actually stumbling across this innovation, and it was something that we didn't set out to design a new method of reinforced concrete construction or bridge system. We were actually in modular housing and building buildings, and we came up with a range of innovations, and one sort of turned into another, and then we sort of thought, oh, hang on a second, like this could actually be utilized for bridges and structures. And so we ended up taking this innovation, and we worked with one of the big engineering firms in Australia, a company called SMEC, and they worked with us to get it to a point that we could actually do a demonstration. And so it was my father, my uncle, and I. We all worked really quite heavily on this, and we built a demonstration on a property back in 2016, and I think it was like the day before we were about to pour the concrete, I sort of said to my dad, I was like, look, what happens if this whole thing falls down, and so we put in place like a range of little innovations to sort of manage that. And it was actually sort of saved our butt having these contingency measures in place, because we're not engineers and we're just thinking about it, from practical terms. We are in the construction sector, but yeah, so we came up with this system, and then we did a demonstration of it, and then we went to market, and as we went to market, we started to see a lot of interest in the methodology that we developed, and it just grew from there. We had a few staff initially, and then it just grew out, and we got to the point where we've built over 200 bridges around the world, and the system's been ranked as the number one bridge system in several different reports, and it's been quite a wild journey, to say the least.
Yeah, and for our listeners that may not be familiar with it, InQuik is a bridge system, and from what I read up on it, it seems pretty cool. Could you explain what it is and how it differs from traditional bridge building methods?
Yeah, so a lot of bridges that are built with reinforced concrete, they're typically built using like fully cast on site methods, whether you prop your formwork and you put all your rebar in position and so on. And the other option, which is also very often used, is precasting of concrete, and it's a massive segment of the market. And there's pros and cons of both options. Like the on-site casting, you've got a very, very good finished product. It's all one mass of concrete. You don't have any joints, and you can create like fully monolithic structures, integral bridges. Whereas, with precast, you end up with the benefits of offsite fabrication and the quality control and, some shorter time on site. But you end up with a lot of joints. You end up with having issues with transportation. Lifting the elements in place is very heavy. And so what our system is and what the InQuik system is we essentially prefabricate the formwork and the reinforcement into modular components. So we take these components and we fabricate them in the shop. Now, a 40-foot unit, which is 8 foot wide, it only weighs 9,000 pounds. And so these elements are so light, whereas if they were full of concrete, you're talking like 60,000 pounds. And so you can bring those in easily. You can install it with an excavator. And the fact that all the formwork's already done and all the rebar's already tied, there's a little bit of tying to do on site, but it means that local skills can install the bridge. There's a lot less quality control on site, and it just reduces a lot of different risks. And so essentially we take the formwork and reinforcement and we prefabricate it in a shop and install it on site, fill it with concrete in position. So we provide the abutments, the bent caps, the deck units, like everything from above the foundation we take in that sort of prefabricated process.
Yeah, it seems like it's what's pretty cool to me about it was it's essentially almost like modular design in terms of the speed, where it's the metal formwork and then you have the rebar cages in there. So all they have to do on site is essentially drop the rebar cages, the formwork, so the abutments, the bridge deck, and then they just pour the concrete. And then it's I imagine it's really quick, right? Because I've done with modular construction for buildings, and the speed of those things is it's quick in days. And I think that's what's really cool about these types of things. Like you were saying, the lifts, the cranes that they need, not a lot, not those big heavy cranes, because they're less than 9,000 pounds, essentially just a rebar cage and some formwork, and then attach it all together, and then boom, it's you got a bridge in a mere matter of days.
Yeah, no, look, it's exactly right, and we have had bridges that have been built from the time they got to site to demolish the existing bridge to the point that they opened the road up, in 5 to 7 days. And so, like a closure of something like that, and we're not talking about bringing in like 50 people to build that. We're talking about like there's three or four people working on that site, and so with the advancements in different concrete and higher strength gain or higher early strength concretes, it enables you to condense that timeline down even further. And so there are still some advancements that are needed to manage the durability of those high early strength concretes, but it does enable you to potentially one day you'll see a ENHANCEMENT bridge get replaced in 24 hours, and they'll be using these high early strength concretes.
Yeah, and structure-wise, it's still a monolithic concrete bridge. The formwork is sacrificial, correct? So
yes,
it's essentially the same design as a concrete bridge, except the construction is a lot faster and easier to assemble and construct. And I know the pain with the formwork in traditional methods, it's a big pain point for contractors. So just getting rid of all that.
Yes, yeah. And I guess to that exact point, so the way that we actually carry the wet concrete weight, which is essentially the biggest innovation behind the system, is we don't use the formwork to carry the concrete. And you sort of get your head around that. We actually use the reinforcing steel. So within the permanent structure, you'll have reinforcing steel in the girders. And what we do is we incorporate a truss into the reinforcing in those girders. And when we fabricate it, we actually weld a truss into it. And we put a camber into the beam when we fabricate it. And then the formwork is hung off the reinforcing. And so because there's a camber, we have to segment up the formwork, because otherwise you couldn't lift the camber up into the steel. And what happens is that the concrete weight pushes down on the formwork load is transferred back up through some bolts that go back up into the rebar. and then the rebar transfers all that weight to the ends of the truss, which is sitting on top of the abutment. So it's a very simple method. The truss is actually disregarded in its permanent state, so it's just treated as a reinforced concrete structure, and it enables you to also get some additional benefits, which are pretty cool, and I'll sort of talk on that a little bit later.
Yeah, I didn't know about that one. That's actually pretty cool. So you're not relying on the metal deck to support it. And I'm guessing that because you didn't want to put any additional supports, right? For, I don't know, 30 or 40 foot span, you don't want to put shoring underneath it. So in order for it to span that, you're actually using the reinforcing cage attached to the metal deck, and you're actually using the steel reinforcing for two methods, for two conditions: the as-built when the concrete's still wet, and then when it's finally done, it can take the typical bridge loads. So 2 in 1.
Yeah, that's exactly right. And when you think about that, an engineer said to me once, like, looking at the reason why no one had really come up with a design around this before, he felt that when you go to university to learn structural engineering, and when you go through reinforced concrete, reinforcement is for tension, concrete is for compression, and everything you do is very simple. Tension is the only method of reinforcing, and compression for concrete. And the fact that we actually utilize steel for tension and compression during the construction phase is where it sort of creates a little bit of a mismatch, because it's when you are doing the calculations, it's not something that has ever been really considered, and so it's quite interesting when you think about it that way.
And what were some of the biggest challenges that you faced in commercializing and developing the bridge system? I know you can't just go from, oh, we got this cool idea, let's just sell it and let's just let's just make a business. I know it's more complicated than that. What was that journey like for you?
Look, it took a lot of picking yourself back up, and really finding the people that see the value in what you're doing. And I guess when you sell products to engineers, it's not like selling it to a consumer who might be, easily persuaded. Like, engineers are the most conservative, especially structural engineers, the most conservative, I think, consumer that you could ever imagine. And so coming into the market with the system and actually showing people the technology, it made sense. Like, they'd see it, they go, look, it's just a reinforced concrete bridge. It's the way that we used to do things, and it's what we're used to. So we ended up raising some of those barriers because of purely that. Whereas if we sort of said, look, we've just come up with this brand new fiber that's made from grass, and we're trying to replace reinforcing bar, it's a long shot. But because we're selling something that they're very used to, they can do all the calculations for it. It's not new technology. It was very, much more willing. But what I will say, though, is that, and I'll use this as an example of the issues you face getting into a market, is no one wants to be the first. No one wants to be the person who puts their head out and says, and I've got a funny story. We ended up actually building a bridge with a county, and the director from the county saw the system, and we hadn't built a commercial bridge yet. And he said, look, this is on a private development, and it was a sporting complex. And they said, look, I really like the system and I want to be pushing for new innovation, etc. And there was a structural engineer whose name was Dave, who was part of the project. And the whole process, Dave was just like constantly like, oh, I'm not, I don't think it's that good. Like, I'm not very supportive of it, all this sort of thing. And like towards the end of the project, I said to him, so Dave, are you happy? Are you happy with this project? And he says, look, I probably wouldn't use another one. And I sort of said, why? He said, he came up with some silly reasons. Anyway, fast forward about 18 months, and we were at this conference, and we had around 30 people that were out the front of our booth, and someone had come over and just gone, "Wow, this is amazing! This is like what an amazing technology." He says, "I've got to tell my mate. I've got to tell my friend." And so he walks off and he brings over this person, and it was Dave. And I was sitting there and I was like, "Oh no!" Like here comes grumpy Dave, and then his friend goes to me and goes, "Mate, this is an amazing system. I can't believe I've never seen this before. Have you seen it?" And Dave turns around and goes, "Have I seen it? Mate, I was one of the first." I thought...
So you do a 180. It's like, oh yeah, I was definitely one of the first people to do it.
Yeah. I shook my head. I couldn't believe that he's just turned around and actually sort of promoted himself as having been a pioneer in trialing this new technology. Now that and
yeah,
so
he's a pioneer.
Oh, no, truth be told, he was not. But so look, when you are going into market with a new product, you've got to understand, what challenges you're going to be up against, and it will take time. Unfortunately, you can't lie in engineering, and people want to see proof and all that sort of thing.
Yeah, I could imagine that. I know for us in the building design industry, when a contractor requests something new, it is everyone's in the office goes, "Hey, I've never seen this before. Has anyone used this? It looks like it works." And then, what we do is, maybe you've run into this, is they ask for all the reports, ICC reports, whatever reports that they need. We need all of that to, all the stuff that you need to convince a structural engineer to, they're eventually going to stamp it. So it makes sense. It's like, we need all of that. Then, and I can imagine getting that first, right, with new technology. It's someone, you just need that one person or that one project to get it going, to show that, hey, it was actually built. And then I imagine you could build your momentum off that. I feel that first one is the tough one.
But in saying that,
gets going after that.
Yeah, in saying that though, Matt, like what I find really interesting is, we built 200 bridges out of the United States. But then when you go to sell it in the United States, it's like, well, if it didn't happen here, it never happened.
Like a really local area.
And I sort of say to them, I was like, look, you do realize that aeroplanes can be made in other countries and just fly over and land in a country. It's the same with our bridges. We can fly our bridges over and it'll still work here. But, some people have their own, micro concerns.
Yeah, related to that one. So starting off in Australia and then going to the US and then even doing some projects in the US. I know in California, what we do is, okay, it worked in a non-seismic zone, but how does it deal with earthquakes? That's our thing in California. It was like, okay, sure, it worked over there in east or the Midwest. What about earthquakes? So then, how do you adapt to these different geographic environmental conditions that's different, not just in Australia, but in the US as well?
Yeah, like any engineer, right? Like you look at what the load cases are for those locations and understand what, considerations need to be made to have a suitable design. And one of the strategies we took early on with our design was standardizing it with a very broad use case. So instead of saying, okay, well, look, we've got these two load ratings and, we've got these types of thermal conditions we've got to consider and these types of flood levels and hydraulic loads that we'll consider, we just sort of thought, look, let's just do it to 95% of the use cases on day one. So we, lifted the design up to a point where in some instances, it might not be as economical, but it's better for us to provide a premium product over us constantly re-engineering it and trying to refine it to meet a lower use case. And so, in Australia, we have a load capacity which is substantially higher than what we have in North America. There are other issues that happen with North America, like the thermal conditions in, like upstate New York as an example. And then again, you've got your seismic requirements. And so we have designed the system to be able to be used in seismic areas. And the only real limitations are going to be on potential issues around detailing. So you might find that we can't do an integral abutment in a high seismic area because of the liquefaction. And you might end up breaking that connection. And one of the things that was quite interesting about that is we've learned so much from a lot of different road authorities around the world as we've been, expanding. And in New Zealand, as an example, New Zealand's got some of the highest seismic codes in the world. And our system's suitable for use in New Zealand. And we actually found out that a lot of integral abutments, when they do the design, they actually design it with no additional capacity through the integration, because if you consider that moment connection at the abutment, and in a seismic event it breaks, you will compromise your structure, and so that's actually been the approach that we've taken since day one. Whenever we use an integral abutment, we never consider the moment capacity, from that connection, because it allows us to use the same deck unit for integral or simply supported. And it also means it simplifies your foundation design because you don't have to consider, the additional capacity in your pile. But it's definitely been interesting trying to understand all the little nuances around it all. And it's not necessarily a one size fits all, but we've tried to take an approach of a one size fits most. And if we need to make some adjustments, we can.
Yeah, I think that's one of the challenges of the industry, where I think your approach sounds like we'll go into these different regions, whatever's the worst case for the most part. We'll see if we can do that as our default, if it makes sense economically. And there's still going to be probably some special cases where maybe a local jurisdiction or a specific code that you just might have to do like a more custom solution for those. But hopefully most of them can get it covered. Seismic zones, non-seismic zones, thermal.
Yeah.
Yeah, I just know, learning even just the American building code and then going into all these different countries with their building codes as well. I was like, oh man, yeah, I have a friend that's doing that. That's international. And he was telling me about all of the different codes that he's learning. Like each code is different, like the UK and India and Australia. But I think the same concept, but there's always those small little details that you need to know about for that specific country.
No, I completely agree. And look, there is, interestingly, and rightly so, there has been quite a standardized approach when it comes to roadway infrastructure and the bridge codes that have been adopted. So you do find like a lot of Asia, a lot of Southeast Asia and things, they do use the AASHTO bridge code. And even Australia, we actually use the AASHTO barrier compliance requirements, and so a lot of codes have instead of reinventing the wheel every time, they've somehow taken pieces out of others, but yeah, it's a minefield for sure.
Yeah, even with local jurisdictions that I'm sure maybe you found out where like a city, they have a particular thing that they don't want to move down. Yeah. I think that's why it's hard to modularize some of these building systems, even for housing, for example, modular housing, modular units. Yeah, that's why it's tough to do it in the construction industry, because you have so many moving parts, so many local jurisdictions. But when it works, it works. I know you've also did some university collaborated with universities. Could you tell us more about that, the research projects that you did, and how has that influenced the evolution of the Inquick bridge system?
Yeah, it's been really interesting doing academic research into the system. And like I explained to you at the start of the conversation, like we came up with this innovation that is very unique. We've got a truss carrying the wet concrete weight. We've got the formwork that's surrounding that. And, is there any composite action between the formwork and the the concrete, trying to look at, what benefits the formwork has to the concrete and the design life of the concrete, because one of the projects we did was actually around the benefits of leaving the formwork in place to slow the curing process of the concrete, because a lot of people, believe that concrete, the quicker it goes off, the more durable it is, and these completely irrational ideas. But what we found through one of the research projects was that the formwork, because it encapsulates the concrete, it stops the moisture from escaping. And so when concrete cures, you get autogenous drying, which is the chemical reaction within the concrete, and then you've got the air drying effect. And so air drying is obviously the gassing off, or the atmosphere sucking the moisture out of the concrete, can give you a lot larger shrinkage and creep over time than what the autogenous drying shrinkage could be. So when we're doing these academic reviews into the system, we're sort of understanding, like, hang on a second, the actual formwork can reduce the long-term creep and shrinkage. It slows the curing process down, so you actually get a stronger concrete over time. And one of the projects was focused on looking at the different concerns or considerations around fatigue and welding of the reinforcing. Because some engineers sort of say, well, look, you're going to have fatigue issues with your reinforcing because you're structurally welding it to the truss, and how does that impact the long-term design life? And so then we did a lot of modeling around that, and then in the field testing and so on and so forth, to just qualify that it's not a concern. Like the processes that we use, the way that the steel has improved over time, as we can demonstrate that it's not of concern, but still, like we were saying just before, like there's so many different codes out there that have different requirements, and so you've got to try to fit within their requirements, even if you think they're wrong. So we spend a lot of time demonstrating why codes are wrong and why they should be rewritten. And I'll tell you now, independent academic research paper does a lot more than a paid consultant, report. Because they look at the paid consultant report and go, hang on a second, you paid those guys, whereas, the academic bodies more so independent. So yeah, look, we've done a range of research and development over time, and it's really played a big part in our overall success in the market by just demonstrating through not only the reports, but full scale testing that the system is what we say it is. And there are times as well, like the modeling that was completed by some of the universities highlighted areas that our engineers had actually had a little bit of an oversight on, and then we're able to sort of integrate those changes back into our design as well, and just to make sure that we have an even better finished product.
Yeah, it's with the engineers, that's the things with codes, right? It may say something, and then sometimes it's up to interpretation. What was the intent of that code? Well, we're using it differently than the way the code intended. And then, if you get stuck with a jurisdiction, all right, give me a test. All right, you got to go through the testing. So, I know that sounds tough in terms of, it's not just, you got a cool product, go do it. No, you got to go through all of these, especially with different jurisdictions. But it seems to be paying off. Once you got all the test reports, then you got those use cases out there. People are more comfortable using it. Contractors like it. So, it seems pretty cool. And I wanted to ask some questions about how does that work? And in the field of structural engineering, I know you kind of mentioned it during the research, but is this a case where, I'm guessing you have your in-house engineers and then they design it, but then they have maybe some of the special detailing that you mentioned before that they may have overlooked from that research, and then they're engineering that? How does that impact the field of structural engineering?
Yeah, look, when you look at changing tradition, I guess, is one of the ways that we sort of put it. You're needing to think outside the box. You're needing to look at doing much more advanced, finite element analysis on structures rather than, just doing a simple, off the head calculation. And so we definitely see that when we go out with a technology like ours and we're sharing the process that we've gone through from an engineering standpoint, and we get a lot of different advice from people. Like, people highlight things that we never even thought about. People have have differing opinions on things, but I really see that there is a willingness within the industry to look at new innovations, to really try to harness becoming more resilient in our infrastructure, having more cost-effective options in the construction of different projects. And it's not like we're getting more and more structural engineers year on year. It's like there's so many different industries that are fighting for really great talent, and so it's important for the whole sector to embrace new technologies and you sort of go back to that modular approach. Like, when you can design a bridge by taking it off the shelf design, having an automated back end so that you can, almost design the same bridge over and over again, it just enables so much more efficiency in the sector, which means that we can deliver on more projects, which means that we can be more efficient on our time. The people that are engaged in the design can actually do some exciting stuff and not necessarily just be working on some, simple calculations over and over again. So, I just feel that the segment, we're seeing a lot more, youthful and excitable engineers coming into the field, and I feel quite excited for what's yet to come.
Yeah, thanks for that, Logan. I know we are pretty slow in the AEC industry, architecture, engineering, construction industry, and yeah, I think one of the whenever there's new innovations coming around, yeah, it's tough to get it in there because of all, I'm sure that you've seen talking about it, all these hoops that you need to go through, versus maybe the tech industry where they just do some new software, and then we'll figure out the legislation later for that type of AI or what. It's like they do it first, and then they'll figure out the restrictions later. But in the construction industry, since there's so many players, I think that players and legislations that you have to get through, I think it makes it a lot tougher. So I think you've demonstrated that, with all the things that you've overcome, innovations can happen. Hopefully it becomes less of an obstacle in the future for new innovations, because I think you're absolutely right. We do need to come up with more non-traditional, more innovative ways to construct, design, engineer. Because I think as an industry, I think we need that, and it'll make it more exciting for young engineers, young people in construction to get more excited about it.
Completely agree.
And finally, Logan, do you have any final advice to structural engineers, maybe future contractors looking to make an impact in the field of structural engineering or bridge construction?
Matt, I've got some pretty good advice there. Having come into this sector with an innovation that was just like by accident, like our journey's been quite unique in all of this. But I feel like the biggest thing I've learned is understanding who is around you and what their drivers are is so important, because when you go and you want to make an impact on engineering or construction or anything, right? And you go to one of your peers and you say, oh, look, hey, I just want to do this. You need to know, what do they want? What are their interests? What are their drivers? Because as soon as you go to someone with an idea or someone, with something that might be new, they might be looking at the job going, look, we're losing money on this, or I'm tired, I've got issues at home, or whatever it is, and they might dismiss you. And I think what's really important is if you want to make a difference, you have to take a strategic approach about how you're going to be successful and how you're going to win. And like, because it's like trying to get a promotion in a job. Like, it's the person that they're always looking at as that's doing the big things and whatever it is, that's the one that gets the promotion. It's never the one that just puts their head down, just works hard. And, so yeah, I think it's just really like, you've got to understand the field that you're in, what you're up against. Because if you surround yourself by people that are similar minded, that want to make a difference, that are innovative, that are really trying to push, like, whether or not it's carbon reduction stuff or whether or not it's creating, like, 3D printers, methods of construction, or whether or not it's, new materials. Like, if you're with people that are stuck in 100 years ago, you're never going to get it done. So, understand who you're up against and put yourself in the right spot, and then you'll be successful.
Yeah, great advice. Knowing what other people want when you're trying to do something new is like, yeah, I want to do this, but I know you want to do this too, so this can help you in X way, versus just here's what I want and it's only me, versus, hey, I'm doing something, it's going to benefit you and it's going to benefit others in the industry, or depending on what they want, right? And yeah, surrounding yourself with the type of people that have that similar mindset, where I can imagine how hard it would be if you were surrounded by people that, hey, I want to do something. I'm not sure. You're never going to get that done, man. And if you're around that every single day, I could see how innovation can die really fast.
Yeah. No, like, we've definitely had many situations. I've met thousands and thousands of engineers since I've gone into this, and when I come up against someone who I'm like, yeah, like, this guy's never going to change, I just pivot, just go around them and keep going. And so yeah, it's for us to continue to innovate in the space, for us to really drive forward into new realms, it takes pioneers. It takes people that are going to pull their socks up and work hard, and be prepared to hear other people say no. Because if you think everyone's going to say yes, don't start.
Absolutely, yeah. The resilience and the tenacity that you have to go through, but all you need is that one yes versus all the hundreds of no's. So definitely respect you for that, and the tenacity that you went through to show that we can innovate in the construction industry. So thanks a lot.
Yeah, great. Really, thanks so much for your time, Matt. And I hope you have a great rest of your day. All right.
Yeah, you too. Hope you enjoyed the episode today. We'd love to hear your feedback, comments, and or questions. To leave them, please visit structuralengineeringchannel.com. There you'll find a summary of the key points discussed in today's episode, as well as links to any of the resources or websites mentioned during this episode. Don't forget to subscribe to Apple Podcasts, Spotify, or wherever you listen to your podcast. Until next time, we wish you the best in all of your structural engineering endeavors.